Hi folks, I'm Prof. Joe. I'm a professor for automation and measurement technology at the University of Applied Sciences in Kempten in the very south of Bavaria. And this is chapter 3 of my lecture on measurement technology, which is AI Tutored. That means the AI link below will teach you all the content, and these videos are only focused on giving you extended information, giving you some special focus on some core topics, and not to teach you the content itself. So feel free to ask anything so that I am able to give you some more videos specific for your questions. Now, what is chapter 3 about? It's called measurement results, and this only means that talking about measurements in common, the last chapters will now talk about measurement results in the sense of having several measurements in a row. Not doing a measurement once, but doing it twice, thrice, or even 10 times, or as often as you want to. Why are we doing that? Because normally it seems obvious that when doing a measurement more often, we get more information about it. That means we see how does it fluctuate, how do all the values spread around a certain mean value. And that's the first thing which is important for us. Now it's the mean of a measurement series, meaning that whenever we have a measurement series, we can just take the sum over the measurements we have and divide it by the number of the measurements. By that, we get a mean value, and everybody seems to agree that according to our guts, this feels correct. But thinking about it more philosophically, it's not clear why to use that mean. You know, it's a chosen definition to take that mean value of our measurements to get a better result for our measurement series we've made. Obviously, talking about it, it seems to be a good definition, a good choice to use the mean. But generally speaking about it, it's not obvious. But let's take that for granted. Let's assume that this mean value gives us some more insight into a measurement series. Now, additional to that mean, we can define the standard deviation using the empirical variance of a measurement. Let's write down that variance just to get a look how it's defined. So again, we get a sum, but now we are summing over all the differences between the mean value and the explicit measurement squared. Again, this seems to be a good definition. Now, defining the standard deviation as the square root of this, gets us to feel that the definition of the sum over the errors of the single measurement to the mean value of all measurements is somewhat, let's say, a measure for the error in a measurement row. You know, assuming we do some measurements along and they all fluctuate around a certain mean value, it seems to be obvious to sum up all of those deviations to get an estimate for the error of the whole thing, for the error which is part of the measurement when doing the measurement series. Now, again, why do we choose the square? That's not obvious at all, but talking about a simple other possible choice, not using the square, we could yeah, we could easily see that such a definition would make no sense at all. So let's just have a look at it, a short glimpse. So let's take the unsquared differences, and we will shortly see we can split up the sum and we get the sum over the mean value in second place. And now we know, yeah, that mean value, it's constant. So we are just summing n times the mean value. So this is nothing more than n times the mean. And now looking at that part over here, we are recognizing that this is part of the definition of the mean. So it's n times the definition of the mean value. So again, this is n times the mean value. And now we see that's simply 0. And now that gives us some justification why we can or should use the mean value. Because we see, in respect to the mean value, all the single measurements and the deviations of the single measurements to the mean value will sum up to 0. That makes sense. That makes sense because now we have a mean value which has the smallest possible errors to all the single measurements. And now that seems to be a good definition, because optimizing for the error, making the error of the result or mean value to the single measurements as small as possible, is a good definition both for using the mean value and for using the standard deviation. Now, this tells us the not squared value would not be a good choice. One could say, now let's take the absolute value of that difference. That's possible, but right now we'll just stick to that definition of the standard deviation, which is squared, giving you the insight that the reason for this choice is based in statistics. It's because of the normal distribution, which implies a squared usage, and which itself is implied by statistics. And that is what we're doing right now, statistics, because we have measurement rows. So altogether, that makes somehow sense. Let's talk about an interesting other fact, because right now we only have defined the mean value and the standard deviation for a single measurement, you know, that is for a single measurement. So that could be used as error for any single measurement we have. That would be all right. To give the user of your measurement an idea of how big your fluctuations around the mean value were. But now talking about the mean value itself, we have some behavior we should look at in more detail. Just let's make some place over here. Why I'm telling you that? Imagine you have a row of measurements. So now on the x-axis we have the number of measurements we've made, and on the y-axis we'll denote the mean. So with each point over here, one additional measurement is made. So we have the mean value for one measurement, for two measurements, for three, and so on. Okay. Now, what does the mean value do? Starting with our first measurement, we'll get just a measurement point anywhere. So the mean value of one measurement point is the measurement point itself. All right. Now let's take into account the second measurement. That second measurement itself denoting the measurements in red, perhaps might be over here. And that results in a mean value which will be somewhat more in vicinity to the beforehand measurement. And now let's go on. Let's imagine there are several measurements denoted here in red all around a certain place. Now, okay, this thing over here will drag down the mean a little more. This will drag it up again. This will drag it in this direction, and so on and so on. And the result for the whole thing is we'll get the mean value and its fluctuations will reduce along with the number of measurements. Meaning, the more measurements we will make, the more the fluctuations in the mean value will be reduced. So with every measurement we are doing in addition, the mean value will fluctuate less. So the mean value will change just a little bit when doing 1000 measurements and then doing the 1001 measurement, meaning one measurement more in comparison to 1000 measurements will not change the mean value in any recognizable way anymore. That's interesting behavior because of what? When we now want to define the standard deviation, the error of our mean value. So before we had the standard deviation for the single measurement. Now we have the standard deviation for the mean value. That mean value, standard deviation, now let's take it as a definition, but the derivation of this assumption over here is very simple. It's part of some training exercises I provide with the lecture contents. And what it tells us is looking at the standard deviation of the single measurement, which is somewhat constant. With increasing number of measurements, that standard deviation will aim towards a value, a fixed value, which won't change anymore. Obviously, because the measurement itself, the errors itself, will give you a mean error in the end. So that standard deviation of the single measurement can be assumed as a constant value. And now this constant value is divided by the square root of the number of the measurements. That means that corresponds exactly to what we are seeing over here. The fluctuations of the mean value will reduce with increasing number of measurements. And that is denoted here. But what does that mean? Doing 1000 measurements, doing 1,000,000 measurements will make that standard deviation, which can be used as the error for the mean value, goes to 0. So that fluctuation error in the mean value can be reduced to 0. Okay, we have an error we can reduce to 0 by just doing as many measurements as possible. But now there are some important differences we have to assume. The first thing is it's the error for the mean value. The mean value is just the sum of all measurements divided by the number of all measurements. It's not a single measurement. So it's just a statistical view on the number of measurements, on a row of measurements. So in its very core, it has nothing to do with the single measurement itself. It does not improve the quality of a single measurement to do it 10 times. We just get the possibility to do some statistics when we are doing more measurements, so that we can, for example, calculate a mean and the error, meaning the standard deviations, for a mean value of a row of measurements. We do not improve the measurements itself. That's an important fact one has to cope with, because, okay, doing a lot of measurements feels good. The mean value won't change anymore, and it seems to be the optimal value, that value which holds the most information about the measurement. To be honest, yes, somehow there is more information in the mean value than in a single measurement. But it is a lot of information is reduced, is taken out by building the mean value of a row of measurements compared to the information in the row of measurements itself. Calculating a mean value means, in the end, to reduce the information given by a row of measurements compared to the information within the row of measurements itself. That has to be clear. So, somewhat the mean value is a little bit better than one single measurement, for sure. But it's not giving you more information or a higher quality measurement value at all. It's just the mean of a row of measurements. It's statistics. One has to think about that every time when using the mean value, that you're not improving the measurement by that, the measurement itself by that. You're just doing statistics to pack a little bit more information in that single measurement value the people are aiming for all the time. So that's due to the fact that people want to have one single value for the measurement, and that should be that measurement with the best quality. That measurement with the best quality, or with a better quality than a single measurement, for sure is the mean value, but it's in the end statistics. It's not more information, it's less information than the measurement row, but thinking about the single value we're giving to another person as result of our measurement, it's a little bit better than just giving them a single value, a single measurement value. Okay, that was part 1. Part 2 will be about regression calculus and its implications for machine learning. If you like that stuff, don't hesitate, just subscribe, and see you in the next part and in the next chapters of this series on measurement technology.